So we are going to wrap up chapter 4 today. There are two little things that it's kind of important that you have seen that we'll go through today, but then we are going to jump into chapter 9 on Monday, which is gas laws. So over the weekend, you need to take a look at the prepare to learn and the vocab. And then after you take a look at it, actually do the assignments and get those turned in by Sunday night. Every year for National Chemistry Week, which is next week, the ACS Club, American Chemical Society Club, does an event at our local library, the Scott County Library, where we have science activities for kids. This year's theme is Picture Perfect Chemistry. And we need volunteers to do the activities with the kids. So I will offer 10 points if you will stay for a little over an hour. So if you'll come at 9:45 and stay until 11, that's just a little over an hour, or from 11 to 12:15. And that way you can either help me set things out or shove things in boxes so we can head out. So I'll offer you 10 extra credit points, and that works out to 1% on your final grade. So that would be like, if you're borderline, that might be enough to push you up to the next grade level. So I have a sign-up sheet here, so you'll be walking by it as you leave. Do indicate on there if you're interested, but you're not sure whether or not you can make it, like put a little star by your name, because I'll try and figure out how many activities we can do based on the number of people I think are going to be volunteering. I try to get two volunteers at a table, and that way, if you have somebody else with you, then you can work with more than one person, or you can bounce ideas off of each other, or if you're waiting for a kid to come over to you, have a conversation. So yeah, that sign-up sheet is there for you at the end. Any questions about upcoming things? Also, as a reminder, the following week, the 30th, is our class day closest to Halloween. If you dress up in a science-related costume for Halloween, then you can get 5 points extra credit for that. But you have to be willing to stand up so we can see your costume and say out loud what your costume is. So I will try to make it as painless as possible. If Dr. Fraley catches wind of it, he's going to have everybody who had a costume be in a picture, just so you know. You are not required to be in the picture if you want the extra credit. I understand if you're like, no, I'm good, I'm sitting down now. Also, as a reminder, scribbling on a piece of paper 30 seconds before classes starts is not going to get you 5 points. All right, so we are going to start with combustion analysis, which is similar to, but not exactly, stoichiometry. So this is something that in the past has been with the material that's in chapter 3, but for some reason, OpenStax needs to put everything in chapter 4. This is a huge chapter that covers a lot of stuff. And I guess because we talked about combustion reactions, they wanted to put combustion analysis in it. So this is actually recording. The 30th. Yeah, since Halloween is actually a Thursday, we'll do it on the Wednesday. Okay, so combustion analysis, of course, involves combustion, which is fire. We are going to use the mass of the products of that combustion to determine the empirical formula. Remember, that's our lowest ratio formula of an organic compound. And organic means it's got carbon involved. And so we talked about this with the balancing equations, that we had a lot of examples that we had carbon and hydrogen. The simplest one was CH4. That's an organic compound. And no matter how many carbons or hydrogens we had, we always had the same products. CO2 and H2O. Now, if we know the chemical formula here, then we can balance this reaction. We can say 1 carbon, 4 hydrogens, 2 waters. That's going to end up giving us 2 oxygens. But the whole point of this is that we don't know what this formula is. So the formula is going to look something like CXHY. Okay, so we don't know what those are. Now we can also do this with compounds that have oxygen or nitrogen or sulfur in them as well, and we get other additional products. We're going to stick with the simplest version here just to see how this works. But even if we get nitrogen oxides and sulfur oxides and things like that, that are other compounds, we will still get carbon dioxide and water. So carbon-based compounds, regardless of what other elements are present, are always going to give us CO2 and H2O. But we can't know what the balancing is. And so that's why it's not exactly stoichiometry. What we're going to look at is not the molar ratio of the balance equation, but the ratio of the atom to the whole element. So what we know is that all of the carbon in here, if we look at the moles of CO2, that carbon comes from the carbon in this compound. So it is related to X, right? Every single one of these carbons, the only place it can go is in here. And the only place I can get the carbon is from here. So it's exactly. Similarly, all of the hydrogen in here is going to end up in water, and the only place water can get hydrogen is from here. So the moles of H2O is related to Y. Okay, so all we need to do is figure out how many moles we have of each of these things, and then we can backtrack to figure out what the ratio is. Now, all we can know is the ratio. We can't know what the molecule itself looks like, and that's why we're going to end up with the empirical formula, the lowest ratio. We're not going to know if it's actually some bigger molecule that just has the same ratio. Okay. That's all I wanted to say about that. So if you had a combustion analysis problem, you would have given to you the mass of the products here. Now, these are both gases, and normally we don't weigh gases, but it turns out that when we do this, we're going to do it in an enclosed chamber, so we're not getting gases from elsewhere, and we're going to run it through two filters. One of the filters is going to pick up the carbon dioxide, and the other filter is going to pick up the water. And so when we weigh the filters afterward, the difference in the weight, this is going to weigh more by the amount of carbon dioxide that's picked up, and this is going to weigh more by the amount of water that's picked up. So that's how we are able to weigh those. As a side note, very first job I had working for a professor doing a little bit of research is what he had me verify. He had sent out stuff for combustion analysis, and so he had me, based on the results that came back, verify what the empirical formulas were for. So it was actually very useful for me. Okay, so everything in chemistry comes down to moles. We want to know what the moles are, so we're going to need the molar weight. From lab, you probably remember this is 18.02, right? This one is 44.01. Now, if I didn't happen to have that in my brain from years of teaching chemistry, where would I be able to find that? Periodic table. I'd look up carbon, I'd look up oxygen, add up their masses. Okay, so I have these two here. And I want to find the number of moles. Am I going to multiply or am I going to divide? Divide, because that's going to cancel my grams here. So in each case, I'm going to divide to get moles. All right, so this works out to 0.00895 moles. But what is it moles of? CO2. Now it turns out that every molecule of CO2 has how many carbons in it? 1. So if I had exactly 1 mole of CO2, I would have exactly 1 mole of carbon. So this number is also the number of moles of carbon. That one wasn't too bad. Hydrogen's going to be a little bit more complicated. So when I plug in those numbers, 161 divided by 18.02, I'm going to get 0.00893 moles. And this is not hydrogen, it's water. Every molecule of water has how many atoms of hydrogen? 2. So if I have 1 mole of water, I would have 2 moles of hydrogen. Okay, so we got to be careful here. Usually when people are doing this problem, this is the most common mistake, is forgetting to change this to moles of hydrogen. So what would that look like? I would say, okay, I'm going to take this number, I'm going to divide by moles of what I have, multiply by moles of what I want, and then I'm going to have 2 on top because there are 2 hydrogens in every 1 mole of water. So that's going to give me my next number. All right, so we took a different way of getting here, but now we're at the same place we were when we did those percent by mass problems. Okay, so on percent by mass, we changed the percent to mass, and then we found moles. And then what was that last step to get us to the empirical formula? We're trying to find the ratio of one element to the other. Divide by the smallest, because a ratio means I need to divide. That's going to tell me how many do I have of this compared to that. So I'm going to divide everything by my carbon. Not surprisingly, this one turns out to be 1. My ratio of hydrogen to carbon, though, works out to be 1.99. Now, when I'm doing empirical formulas, this is where sig figs are a little less important because I'm really trying to figure out what the whole number ratio is. So that's really close to what whole number? 2. So this tells me that I have 2 hydrogens for every carbon. So my formula then is CH2. Okay, so that's the basic idea how you do those things. I am never going to put this on a test unless it is like a bonus question, which I probably won't even do that because there's too much to test you over anyway. But now you have seen it and you know how to work out those kinds of problems if you need to do such a thing in the future. So it may come back again in organic chemistry, but there you go.